Gonna continue. Welcome back, everybody. Name's Theo again, and we're going to continue our discussion on the Navier Stokes equation. So in the last video, we have come up for our x direction momentum to this point, and now we want to find some correlations to help us determine what this stress, this particular shear stress and normal stresses are, so that we can simplify this Navier Stokes equation to a form we can easily use. Now, here are the constitutive equations. Constitutive equations. Alright, for now just bear with me. I'm just going to throw some equations at you. Tau zx equals tau xz mu partial plus okay. Note, the assumptions here are Newtonian fluid, mu okay, maybe this one's too early. I'll just say this is by Stokes. Okay, so that's tau zx. Now let's take a look at sigma. Now these are some of the correlations that Stokes actually came up with. So let's look at sigma. This will be 2 mu partial u partial x minus 2 by lambda blah minus p. Here lambda is 2.3. We should put a plus here. Now you might be asking, where did this all come from? Now, if you really want to know where this comes from, there is another complicated set of derivations that we must do in order to derive all these equations out one by one, slowly. And of course, all these have to be kind of, there's some experiments that actually go on to determine what this value of lambda is. Yeah, so it's partially a mixture of some theoretical things that we've been doing. It's very similar to this control volume analysis, but yeah, it's a little much to go on now, so you just have to take it that these are the relations to be used. But if you really want to know where all these actually come from, just leave a comment in the video description, and if I have time, I can try and do it for you in future, like as a supplementary kind of a video. Now for now, just take it as it is. And if the said supplementary video does come out in future, I'll post it in the description so that you can see what you need to see. Alright. So this is just how to say, so-called copy and paste. Alright. So Just some common patterns to note. This is, if you're talking about normal stress, this is a x velocity, x direction. This is kind of common throughout all three, and then there's a pressure term as well. Well, pressure is actually force per unit area, so you would expect it to pop up in this what do you call that? Shear stress. No, not shear stress. Normal stress. And since normal stress is pointing outwards, pressure usually points inwards. They are oppositely signed. The signs are opposite. And of course, if you look at the shear stress, then if let's say you have a tau zx, this is the z velocity, this is the x direction, this is the x direction, this is the z velocity. So you can see some sort of pattern here. Again, this should be a v. If this is a y and x kind of a thing, kind of a shear stress, there's a x direction velocity, y direction velocity, x direction. Okay, so now I'm going to just copy and paste all of these in. Okay, so here we go. I'm going to copy and paste. Okay, just going to paste one more time here. Alright, so this is what derivation looks like. It's a bit messy. Minus 2 over 3 mu. Okay, that's one. Here will be this. That's tau zx. So I'm just going to copy and paste this in. It's just normal substitution, nothing more than that. Tau yx is just this. Alright, so this is what the, okay, this, well, let me try getting rid of the highlight. Yeah, now this is what the Navier Stokes equation looks like for yeah, this is the momentum balance for if we assume the shear stresses are determined by Stokes Constitutive Equations. So basically this Stokes guy, he did some derivation and experiments and found out this was the relation. Now we'll make some further assumptions to simplify this. Now we assume constant viscosity. Now this is what I was saying earlier, Newtonian fluid. Okay, so let's assume constant viscosity. That means this mu is actually constant, and I can just bring it outside. Okay, 1, 2, now just take this out. And I'll bring this pressure term out of the whole thing. I just want minus. Okay, I'll get the pressure term out. And I'll factorize this out as well. And now I'll just apply the partial derivatives inside. So I'll just take the partial u out. Square partial 2u. So these are second derivatives. Take this out. 1. Okay. Next. partial u partial x will come out. Okay, I've dealt with the first terms. The first terms are here. So, no, I'm not going to highlight. Yeah. Second terms are like that. So I'm just going to copy and paste twice. So I'm going to have a plus here and do this. First I'll delete this and then I'll delete this. And it's easier for us to see. Partial square u, partial 2u, partial x squared. Alright. I'm just going to try and trim down the equations. Okay, this one I will leave it as it is. This one, okay, there should be a mu here. Okay. Let's see. This one also, I'll just copy and paste another time. There you go. And then I can have a partial square, partial 2u partial y square. 2u and partial y square. Alright. And then the other thing I want to do is this, just to simplify it for us even clearer. So I'm going to split the term like so. Now why am I doing this? You'll see it very shortly. Okay. So I'm going to group 3 of the terms together. So once here, okay, I'm going to rearrange once here. I'm going to paste it here. Okay. So 1, 2, and 3. Then the rest are kind of so-called leaving it alone. So these 3. What can we use? We can actually use the something like what we have done before. Okay, where's the no highlight button? No color. Yeah. So nabla or the divergence. Remember this operator was the partial. Okay, I'm not going to write it out. I must have written it out earlier. So remember this operator. So I'm going to write recall. So remember what our divergence operator was? Now we can do it twice so that we can use it to represent this thing. So let's write. Now we introduce this term. Blah square equals to same thing. Partial square. So it's a second derivative with respect to x, y, and z. That's all that we are doing. This is the operator that we use. So I'm going to use this and simplify this side. Okay. Similar to how we are doing all these substantial derivatives and this del operator. If not, our equation is going to be terribly long. So all I'm doing is just to make the equation neater. So mu nabla square u. Or del square U. This is all that it's saying. Sometimes you might see people use this notation. It basically means the same thing. See, the divergence of the gradient is, okay, what's the divergence? Divergence is this, del dot. And what's the gradient? Gradient is basically in a, okay. So let's write square equals to nabla bullet nabla. So we'll have a del by del x, del by del y, and del by del z. Okay. So we are doing this just to make it neater, if not the equations are very long. Alright, so it will just end up being the same thing. Okay, that's all we are doing here. Nothing more than that. Alright. Yeah, and so that's all we are doing there. I prefer, of course, to use this notation because I don't like having too many triangles. I just like this square. It's much simpler. Now, this thing, for this, so this is something to know about partial derivatives. The order of differentiation doesn't matter. Okay. Now you'll see why I'm doing this in a very short while. Okay, so I'm replacing this derivative with something like this. Okay, and the second one as well. There's a y. There's a y and a v here. So v and y. So again, I'm going to replace these two derivatives with these terms. Now, yeah, this is something I'm also not going to go through in this video, but you should already know, doing this partial differentiation, no matter how you do your derivatives in the partial differentiation, it doesn't really matter. So I'm just gonna copy and paste it here. Alright. And then I'm gonna rewrite this like so. Now, why am I doing this? Again, we can make it neater. We can factorize out all these terms, 1, 2, and 3. Why can we do that? Because they have the same mu and the same derivative. And let's find out what's inside each of them. So I'm going to factorize that and combine it together. So 1, and then this one is number 2. Now what do we notice about this? This is also a divergence kind of a thing. We can rewrite this. So 1, 2, there we go. Nabla dot, or we have a bullet. It's just the divergence of a velocity. So this, so I have not made any assumption, but except that it's a Newtonian fluid. So for Newtonian fluids, compressible or incompressible, the equations are this, 1. And then we have our mass balance as well. Whereas our mass balance should be somewhere on top. There you go. That's our mass balance equation. Yeah, that's our mass balance equation. Is this our mass balance? Yeah, I think so. This looks like it. Yeah, this is our mass balance equation. Yeah, let's bring it down. So let's bring it down in here. So of course you have y and z directions, and the procedure is exactly the same as what you do for the x direction momentum. So I'll just put there. There will be y and z direction equations as well. What would they look like? I'll briefly type it out for you. Okay, not going to derive it because the principles used are exactly the same. Again, if you want me to derive it, please leave a comment in the section, and if I have time, I'll go and derive it out for you. Then I'll put the video link if I've actually done it. Alright, so just leave it in the comment section if you want me to derive it for you. Otherwise, I won't be deriving it for you. So, in the y direction, this will be what it looks like. You just change it to v. Change to the partial by partial y. Oopsie. That should be y. So this will be del p del y. And this will be gy. And of course, this will be v. Okay, so all I've done is to change the derivatives from x to y. Of course, the g will be in the y direction, and the velocity is changed from x velocity v u to y velocity v. So same thing for z velocity. That makes it very easy to remember. Much easier than if you try and derive everything out. So it's just del by del z, change all the y's into z's, and all the y velocities into z velocities. That's all we are doing. 1, x direction momentum, y direction momentum, z direction momentum. And why am I not changing this divergence of u? Well, because this thing actually represents, you see, where did it come from? U, v, and w. So it's kind of universal. U equals to u, u, v, w. So no matter what, you have all these three components in there. Okay, so it doesn't change from equation to equation. That's how I remember it. Okay, so these are Navier Stokes for Newtonian fluid. Okay, these are the Navier Stokes. I'm just going to highlight this in green. Okay, now for incompressible fluids. Now this makes the Navier Stokes equation even easier. So 1, mass balance, 3, momentum balance, 2, 3. Okay, I'm going to remove the highlight. Alright, so we'll have a incompressible. Means density is constant. So what does it mean when density is constant? Well, it means that you can factorize this thing out. 1 rho, and then you can factorize this density out also. What does it mean? It means here, this whole thing here becomes 0 because differentiating 1 just results in 0. Okay, so I'm just going to delete that. And then I'm going to get rid of this as well, because I'll divide both sides by density. Because density cannot be 0, so I can divide both sides by a finite number. So in the incompressible fluid, divergence of velocity is 0. What does it mean? It means this 3 terms, delta x, delta y, delta z, equals 0 for incompressible fluid. And then look at what it means for our momentum equations. Alright, this is 0 because divergence of velocity is 0. This is 0, divergence of velocity is 0, which means good news, we can cancel more terms. Boom. Okay. Alright, so we see, well, so for incompressible fluid, we have this 4 equations. Hopefully it's easy to remember. So you have this del square term, pressure term, gravity term, and then this total derivative. Just 4 terms for you. If you want to write it in vector form, it's even easier. So you just have mu how do I write this? Okay, there's a Wikipedia page on that. Alright, I'm so sorry, I have to refer to Wikipedia. Okay, Stokes equation. Can't remember exactly how to write it. Yes, but this is what it would look like. So these are the derivations. We have gone through them before. Oh yeah, incompressible Navier Stokes equation. Can you see this? So you can see this is the total derivative part, du dt. This u is actually the x, y, and z velocity in vector form. Okay, so this is from Wikipedia, yeah? I'm not going to, but this is the vector form. And it looks like it's divided throughout by density as well. Okay. So this is what it would look like in the vector form if we divide it throughout by density, okay, because density is constant. Then this is what we will get. What is del dot w? Yeah, stresses. These are stresses. So this w is probably got to do with the pressure. Okay, so anyway, if you forget things, just remember these 4 equations for incompressible and these equations for compressible and incompressible Newtonian fluids. Alright, so these are the Navier Stokes equations. Hopefully it's not too difficult to remember and use them. So probably in the next video we want to look at solving some problems with this. Thanks for watching.